Great. Thanks everyone for coming to the last scale session. Uh, so the topic for this presentation is unusual ways of using application checkpoint restore. And my name is CRIU. I'm with Virtuosa. And the agenda of this talk is, first of all, we'll see what checkpoint restore is and what checkpoint restore in user space is, and then we'll go on to see the default application for checkpoint restore, which is live migration, and we'll see some other interesting use cases beyond the live migration. And finally, I'm gonna introduce you some of the software that we either just released or about to release. That is also very relevant to checkpoint and restore. A few words about myself. My name is CRIU, and Kirill is just a Greek version of Cyril, or Cyril as they say in France. There was a guy who invented the Cyrillic alphabet, Kirill. So this. I always have problem for people to call me by my name, so I have a few alternatives for you. First of all, you can always call me by my Starbucks name, or by my seafood name, which is not shrimp, that is krill. All right, but well, I'm doing containers since, before the modern world appeared, and I'm mostly known by leading the OpenVZ project, that is containers before the term containers appeared. I led it right from the start and still leading it today. Also happen to be a veteran speaker and exhibitor at scale. My first scale was 4X in 2005, and well, I had a few emissions, but there's a lot of scales for me. I'm originally from Moscow, Russia, and I'm now living in Seattle, Washington. And these scales that are marked in red, that are the ones that I visited from Moscow, came to speak or exhibit or both. And the blue ones are from Seattle. So I'm going to talk about checkpoint restore in user space, that is CRIU. Well, you can say CRIU, but somehow we decided to call it CRIU. And the story of CRIU goes as follows. About 2004, then we were working on OpenVZ containers. We had our own kernel, our own fork of the Linux kernel, and we implemented checkpoint restore for containers to be used for live migrating those containers between machines. And one goal of the OpenVZ project was to merge as much containers functionality as we have in our own kernel upstream. And we succeeded with quite a lot of stuff. I mean, currently you can run containers on vanilla kernel. That's partially due to our work. The biggest piece was probably network namespace, then process ID namespace, some C groups functionality, etc., etc. But it didn't happen that way with the checkpoint restore. It never got accepted. We just failed miserably. It was in kernel code. It was pretty complicated. It touched a lot of different file systems in the Linux kernel, except maybe for drivers. So each and every subsystem maintainer hated us for sending this code, for making their nice little code crappy and bloated by the checkpoint and restore. So we decided to get around it and implement the same functionality in user space. That was a crazy idea, but now, after 4 years, we can definitely say that it works for us and it works for everyone else. So the main idea here is to use /proc file system to gather some information about the processes running. There's a lot of info in there about the process, so we can checkpoint them by using that information. The other thing is we can use some debug facilities, and we also use some other mechanisms that I'm about to tell you. That worked, but in some cases it requires a few kernel patches. So far we have about 200 kernel patches that are merged in the scope of the CRIU project in the Linux kernel. And starting from, I don't know, like 3.11 kernel, CRIU works on that kernel. So in some cases, then there is no info in /proc. We had to patch the kernel, add some mechanisms, so on and so forth. Well, I should have clicked the space, right? So another thing is currently CRIU is like a low-level tool. It lets you checkpoint and restore, and it's of use. I mean, it's of no big use by itself unless you're doing some advanced thing. It's better to be integrated in some other things. And so far, CRIU is integrated in Virtuoso and OpenVZ. It is now used for live migration and checkpoint restore instead of that old in-kernel implementation that we had. It's also integrated in Docker. I don't remember which version though, but you can now say Docker checkpoint and Docker restore, and it uses CRIU to checkpoint and restore a Docker container. Also integrated with LXC and LXD, same thing. Integrated in runC, which is a low level of Docker, and so on. There are some more projects. So we are very well integrated. As for CRIU itself, we are currently at version 2.11, and we are doing predictable monthly releases. So mostly it's to make the whole process predictable and make the distro vendors more happy, so we know the date of the next release, and so on. So let's take a look at what checkpoint is. Now, the objective of checkpoint is to collect the complete state of a set of running processes, everything that the processes are, in order to be able to recreate that state later in a different place, maybe. It all starts with freezing a process tree, so the state is fixed and it's no longer changing. So first thing we do, we freeze the process or a process tree or a container. Next stage is we carefully collect and dump the complete state of these apps of a container. That includes lots and lots of things. Opened files, sockets, pipes, all the established network connections, all the undelivered signals, all the memory mappings, CPU register, credentials, UIDs, GIDs, all the truths and the HDRs and all these timers. There's a lot of things to collect. And we collect it all and we save it to image files, just some files on disk. And we use three mechanisms, as I mentioned earlier. First of all, there's a lot of info available from /proc. We use ptrace debug mechanisms for some stuff. Finally, we have very interesting thing that we call parasite code injection. There is certain information about a user space process that can't be obtained by anyone else except this process itself. That includes the process memory. That includes only some other things too. So at some stage of dumping, what we do is we have our own very small code that we call parasite. We inject that code into a process and we let it run on behalf of that process. And it collects some things for us. The author of the original idea about the parasite code injection is Taeyoon Heo, who, if I'm not mistaken, delivered a presentation this morning right here in this room. So kudos to Taeyoon. Finally, we collected everything and we can now kill this process set, or we let it run, we resume it. It depends on what we want to do. So this is a very simplified view of what checkpoint is, and the details are available at our website, CRIU.org/checkpoint/restore. Restore is the same thing in the opposite direction. We have those image files with complete state of the processes, and we recreate those processes. By morphing itself into this set of processes. So CRIU runs, reads all the image files, figures out which resources are shared, like there can be an open file descriptor which is shared among a few PIDs. And we cannot do open 3 times. We need to do open just once and then, inherit a file descriptor through inheritance. So we need to, at this stage, we need to carefully figure out which resources are shared and what is the proper order of creating those resources because of proper inheritance. Next stage is we actually go ahead and fork the process tree, all the process that needed to be there. We just do the forks. At this stage, actually, we had to recreate the exact process IDs because PIDs are not, you cannot change PIDs. So we have to recreate exact process IDs and so on. And when we restore some basic resources like those open files, we jump into the namespaces. If there are any, we recreate private virtual memory areas, sockets, all the HDRs and struts. Finally, there is that little thing that is called restore blob. That's another small piece of code, not unlike parasite code that we have for checkpointing, but it exists here because currently what we have, that process tree we just created, it's CRIU. And we don't want any traces of CRIU in there. So we need to unmap all the CRIU stuff and map all the stuff that has become the application. So we need some intermediary code to unmap the CRIU and unmap itself, and then it becomes what we restore into. And that restore blob also restores some particular resources like timers, for example, so they won't fire prematurely. It restores the exact mappings, and it restores credentials because for some things that we've done before, we needed root. Now we don't need it, so we do set UIDs and so on. And it also restores threads. Again, it's a very simplified explanation of what restore is doing, and the details are on that URL. Now, the default application for checkpoint and restore is live migration. And live migration works on top of checkpoint restore and works like that. We freeze the processes or container, let's say a container, and we checkpoint it. Then we copy everything to the destination server. From server A to server B, we copy the container file system, container files. we copy those CRIU images we just created, we copy some metadata, I don't know, Docker config of a container. And on the destination system, we run the restore, and we unfreeze this, and it keeps running. So here comes the live migration. You can, move, I don't know, a database server. You can move pretty much any container that is not directly tied to some particular hardware, and containers are usually not tied. You can live migrate any set of processes that you wish to, if it's dumpable and restorable. There is something wrong with this live migration. Any guesses, maybe? Okay, I'll give you a hint. It's not really live. This copy stage, it takes a lot. And during the copy, the container is frozen. It doesn't appear to be live. It's not dead, not exactly dead. It's still there, but it's frozen. So we have some tricks up a sleeve to make live migration much more live. And one trick is to use iterative memory migration. That is, a lot of that data that we have to migrate is just application memory. You can, run a huge database server occupying a terabyte of RAM, and we need to copy that terabyte over to a different server. And as this terabyte of memory is not really changing every second, what we can do is we can dump the memory of a running set of processes, and then we copy that memory over, and our server is still running fine. And then we do the dump again. This time we dump only pages that were changed. So this is one part where we had to modify the kernel to support so-called soft dirty bit, that is dirty memory tracking. So we can ask the kernel, please keep a list of the pages that are modified, and then we dump everything, and then we ask for that list, and then dump it again, and we do so iteratively, hoping the set would shrink, and it usually is shrinking. And finally, at some stage, we decide to freeze it and do one last dump, which would be way less than 1 terabyte. We do one last dump, and then we, copy and restore as usual. That way, we can save a lot, and in the frozen time from minutes to maybe seconds. There's yet another approach to it. It's called lazy migration. So you either use iterative migration or the lazy migration. So iterative migration is then we pre-copy the memory. Lazy migration is then we post-copy a memory. Instead of copying everything, we just copy the freeze and we copy the bare minimum. And then we unfreeze the container, but it doesn't have a lot of memory itself. Before unfreezing, we set up sort of a network swap device, with swap being the source server RAM. And, then it tries to access those pages, it gets page faulted, and those page fault handlers, they go to the source and fetch those pages. And in parallel with that, we proactively migrate those pages. And the app is already running there. So that's another way to reduce the frozen time. It's still a work in progress for CRIU. There are people working on it as we speak. And it's implemented through the user fault FD feature of the Linux kernel. Now, yet another trick to make live migration more live. I'm not sure if this is very visible, but this is what we do in order to copy the data. Then we do, first of all, we do CRIU dump, and we write files to the disk. Then we do like SCP or rsync or whatever to copy the data over to the destination, meaning we read everything from disk and we write everything on the disk on the destination. Finally, we do CRIU restore that reads the data from the destination disk. As you can see, the problem here is we do twice amounts of reads and twice amounts of writes, and it's slowing things down, especially taking into account that disk I/O is not, you know, blazingly fast. So we can use a couple of tricks to make it better, and it's called diskless migration in our lingo. Before doing migration, we either use existing or mount our own TMPFS instance, which is basically a file system in RAM, so we don't have to do any disk I/O. And we run a very simple thing that is called CRIU page server that just, you know, receives the pages and writes them to that TMPFS. And on the source, we say CRIU dump or CRIU pre-dump in case of iterative migration, and they say don't dump it to the disk, dump it to the page server. Here's the IP, here's the port number. And it dumps it right there to the destination. And it goes to RAM. And then CRIU restore just reads it from TMPFS, which is a memory-to-memory copy. So no disk I/O, and no double reads, no double writes. I could probably talk about live migration for hours, but there is just one final thing I want to tell. CRIU is not a live migration. CRIU is checkpoint and restore. It can be used for live migration, right? And the full live migration is done by another tool that we have, and it's called p-hole, process holer. There's a little humpbacked horse that, you know, carries your process around. It's criu.org/p-hole. And that concludes my presentation. Just kidding. Beyond the live migration. If anyone read the description of my talk, you know some of the scenarios that CRIU can be used for. One such scenario is a save button for a game that lacks one, so before going around the dark corner, you just do CRIU dump, and then you can return to this place. And you can obviously do so with any other app. If you run, I don't know, some kernel compilation and forgot to move it to screen, you can checkpoint it and run the screen and restore it inside the screen, or tmux. You can save a state of the long job. That is not for the same thing, but it's not for the game. Consider you are in bioinformatics or that sort of thing, and you're running some huge data number crunching, like, I don't know, protein folding, and there's an application that does a lot of computation, and it takes weeks to, you know, finish the task, and the power goes down, and you lose weeks of work. So you can do periodical checkpoints, like every half an hour. Worst case scenario, you lose half an hour of work in case of some disaster. So this save the state is for HPC stuff mostly. And then you can always do load balancing within a cluster, move your containers around in a cluster in order to balance the load better on your system. And of course, it's migrated together with the network connection, so your users won't notice it. This is a live migration application, of course, not a specific CRIU migration. And then there's that thing I don't have a good name for, so I went for open heart surgery. The idea here is to do something with images in between checkpoint and restore. So you checkpoint your process tree, you checkpoint your container, then you go to those image files and you modify something. You modify a file name that is opened, or you modify some ID inside there. So we had a tool for that, it's called crit, and it lets you basically convert those binary images into, say, JSON, and then you can modify the JSON and convert it back to binary. And then you restore not exactly what you have checkpointed. Sometimes you have to, there are some funny cases then you want to do something like that. And I'm calling it open heart surgery because actually this is like a live patch, and you checkpoint, change something, then restore, and it keeps running, but it's a little bit changed now. Anyone from the audience have any other scenarios in mind? Any cases? Yes, please. Mm-hmm. Well, Docker image format is just a file system. And what we mean here, we don't save a file system. CRIU doesn't deal with a file system. We save the state of the running process. Of course, to do live migration, you need to copy those files over. And in order to do a successful restore, you have to have the exact state of the file system. Like if some file is changed or lost, you might not be able to do the restore. Fortunately, we have like file system snapshotting mechanisms for that, and this is like out of scope for CRIU. So you can use like DM snapshot for that, for example. There's a feature of the Linux kernel. Or you can use ZFS snapshots for that. Yep, yep. Yeah, basically that means that you can like pause and unpause everything, or yeah, that's right. Yes, please. Uh-huh. Yeah, of course. Yeah. You can have some like state that you want to start from, and you start right there from the state instead of recreating it. You restore from it. Right. Right. Good. I'm actually going to talk about this case. Yeah, I have a whole slide about this case. That's great. Yes, please. Right. So you mean instead of starting from scratch every time, you can start from some intermediate state? Uh, Right. That applies to simulation on some networks. That can also apply to some QA work. Like there is that specific state you want the application to be in order to be tested, and it takes a lot of resources to go into that state. You need a lot of steps and dances around for the app to be in that state. And the next time you want to test it, you just test from the checkpoint, and it's the same. Yeah. Good. So I had a few more cases like that, and a little bit more details. The first case is really very unusual. We use CRIU to test the Linux kernel. The thing is, CRIU is pretty advanced software. It does a lot of things with the kernel that no one else does. And the other good thing is we have pretty extensive test suite that comes with CRIU. And it's like I don't know, a few hundred test cases that are run in different scenarios. And of course, we use this test suite to test CRIU to make sure that we don't, break everything, and we test it on the stable kernel to check if if CRIU is still working for us. But we also use the Linux Next from Git, that is to become the next Linux release, and we run the same tests on stable CRIU this time to find potential bugs in the kernel, potential regressions. And so far, we have found more than 10 kernel bugs this way, just by running some Jenkins jobs with Linux Next Git report. There's that URL CRIU.org/Linux Next that lists some of those. Then we decided that we need to document those cases. Next thing, let's call it time travel, or if you want to be less fancy, that is reverse debugging or rewind. Well, same thing basically. You do periodical checkpoints, and in between you do some work, and then you can restore, rewind, time travel to any old state. A good example is that runkit.com service, which I believe one of CRIU developers work for runkit. What they do is some web environment for JavaScript developers. And they do have that big rewind button. So is a quote from the website. Runkit takes time travel in debugging further using the revolutionary new technology called CRIU, which allows notebooks, that's JavaScript applets, to snapshot the entire environment. That means you can rewind sub-processes, the file system, really just about anything in your session. Of course, as I said before, CRIU doesn't care about the file system. For that, I believe they use DM snapshot or something like that. Speeding up applications. Instead of starting the application each time from scratch, you just start it once. When it's fully initialized, you checkpoint it, and next time you use restore instead of start. Well, that's, I believe, the same thing as Josh mentioned about doing demos. We did a quick test with Eclipse IDE, which is famous for starting very slow. It takes about a minute and a half to start, and it takes about 15 seconds to restore. And in both cases, we had the very same state of Eclipse. Yes? Uh-huh. Oh, right, yeah. You want to restore the SQL server in like a hot state, and its cache is already filled in, right? Uh-huh. I see. Yeah, that's right. I know someone who's using this mechanism for Apache and PHP. It's probably because there are a lot of modules in PHP, and it, does lots of reads and then places these modules in memory, do some linking. Interesting thing is, it's faster to just restore it. And one last scenario would be the booting of the mobile phone. Like you can boot it once and checkpoint it, and during the last restart, instead of cold start, you can use hot restore. I'm not sure, but I think either Samsung or Huawei was working on something like that using CRIU, although I don't know any details. This scenario was also mentioned. This is the deferred or remote debug. We actually talked to Nginx guys, and they said they have that big problem, like, I don't know, they have some big bank as a client and a pretty expensive 24/7 support contract, and then the Nginx server misbehaves, they want to debug it. And the client, of course, want to restart it. And then there is a dilemma. If you restart it and this bug is not fixed, it will resurface and it will bug you. If you debug it, that means downtime. Well, you can alleviate it, of course, but sometimes not. If it's like a front end or something, the only choice is to restart. And then, yeah, you can checkpoint it, and then you can have both restart and debug using those saved image files. Same thing as Josh mentioned as forensics. Another pretty weird scenario. We use Travis CI extensively to test CRIU. Anyone in the audience using Travis? Okay. Oh, well. You guys. So Travis is awesome. I love it. But one problem is they only provide that specific, that old version of Ubuntu, 16.04. And what we want to test some of the latest kernel stuff that we added recently, we want Ubuntu 16.04. And we want like a latest kernel. And you can have neither. You cannot have your own kernel, you cannot have any other distro with Travis. You're locked. You can have it in container, but you cannot run your own kernel. So the initial idea was pretty simple. Just upgrade that Ubuntu in place. You just, change trusted to denial in sources, let's do apt-get upgrade, apt-get dist upgrade, and then you need to reboot into the new kernel. The problem with this approach is there is that specific control process that Travis runs to keep control of the VM, and once we reboot, the process is gone, and Travis loses this VM, and it thinks it's not existent. We cannot do anything, it becomes unusable after reboot, and I guess some garbage collector code just kills that VM sometime later because it's lost. The idea is to make that control app survive a reboot. It has the network connection to Travis, it's like an SSH session, and then they run something under that SSH session. So we can do all the same thing, but before rebooting, we checkpoint the Travis control app. It's not an app, it's like it's a small tree of processes. And then we restore it. It ended up not as easy as I'm telling you. There are some interesting workarounds that we had to implement because with the massive upgrade from 14.04 to 16.04, pretty much every file on the system is lost, is replaced by something else. Then there are a few things, but this is the article that describes all the magic tricks that we had to implement, and it took about a day to make it work, but it's working. So in a sense, we hacked Travis VM, and we can now enjoy running latest and greatest Ubuntu plus our own compiled kernel in the very same environment and use this fantastic Travis server. And it's working, and the good thing is we already found one particular kernel regression using this testing in Travis. So there was a fix that came in 2 patches, and the subsystem maintainer applied the first patch and didn't apply the second one, so it got broken, and we found this exactly using this scenario. All right, that concludes the part about different use cases, and now I'm going to tell about a couple of things that we're working on lately. libsoccr, which is socket checkpoint and restore is a library that I'd like to tag as Lego for TCP sockets. What it does is checkpointing and restoring of TCP connection, of the established TCP connection. TCP is pretty complicated, and it takes a lot of effort to be able to checkpoint and restore TCP sockets. So we had to, this is yet another case that we had to patch the kernel for it to work. We introduced so-called TCP repair socket mode that basically lets you recreate a socket without any network activity. It's like when you can do send, and it's not sending anything, it just fills in the buffer. You can set various options, but that doesn't lead to any network activity. So CRIU uses this TCP repair feature to restore network connections, to restore TCP sockets. And then we figured out that CRIU might not be the only user of the feature. We took the code from CRIU and ported it out to a separate nice library which does this thing for you. It's basically a library for the kernel functionality that we have. And it's part of the CRIU now, but it's a separate library. So if you're only interested in moving network connections between machines, or checkpointing and restoring network connections, or doing some tricks with network connections, the opened TCP sockets, you can use this libsoccr thing. One scenario is you can have a front server accepting network connection, and then it moves it to a different machine, and then someone else works with it. And you don't have to use the full CRIU load for that. Then there is another thing that we ported out to a separate library, and it's called compel. That's that parasite code injection thing I mentioned earlier. That's the parasite code injection for the masses, so anyone can do things like that. With compel, you can do two things. You can perform system calls on behalf of someone else, or you can run your own code inside someone else's process. And this is what we use during checkpoint stage. This thing is currently in development, and it's only available from the CRIU dev branch, but we are going to finally release a development preview of the feature this month in CRIU 2.12, or you can, just check out the CRIU dev branch and cd compel and see what's going on about it. Again, this is still a work in progress. We can change the API, so please don't rely on it being stable. It's 0.1 at the moment. And there is much more info about it at criu.org.compel. I'm not sure if we have much time left. If we do, I can show you a simple case of using compel. So you include compel/compel-h, and then you do this. You call compel stop task to freeze the process identified by PID. Then you call some magic called compel prepare that prepares the process to be victimized by our parasite code. Then we can immediately execute some system calls inside this foreign process. In this very example, we execute close this call. So we close any file descriptor inside any process. Finally, we run compel cure to cure the victim, and then we resume it. And once it's resumed, that file descriptor that was opened is closed now, is now closed. I'm not sure, maybe it will crash, maybe it will figure something out. But this is a good way to, for example, do some fault injection. Actually, nowadays, strace can do fault injection as well. But yeah, this is another way of doing it. So that's as simple as that. And the blue stuff here is preparation and, rollback. Executing your own code inside a foreign process is a little bit more complicated. I mean, we tried very hard to make it as simple as possible. Oh, one final thing. You write this proggy and you compile it with some specific includes, and then you link it with some specific libraries. This is how you do it. If you do it from the command line, well, makefile example is similar. Executing your own code that we call parasite code. First of all, of course, you need to write it. You do some proper includes, and then you have to have this function, which is like the main for a parasite. It's called parasite daemon command, and it has two arguments: the integer, which is like a command, and then some pointer to some data. And you can do it like this. If command is close, then you return sysclose, and the pointer, that pointer is the pointer to the integer, which is the file descriptor name, and so on and so forth. So this is the very short example of the parasite code we're going to inject. Once written, we need to prepare it. First of all, we compile it with some specific C flags, because there are some things that GCC wants to do for us that we don't really want in the parasite code, so we have to disable something, enable something. That's all hidden under compel C flags. Then you link it with some, not C flags, but LD flags, of course, and then we link it together with some plugins that I'm going to tell about in a minute. And finally, as a result, we have some binary blob. This is our code compiled and ready to be injected. Finally, currently it works this way. You generate a C header that contains this blob as well as some auxiliary functions for this thing to work. And we end up with parasite.h, which contains that binary blob inside it. Now we are ready to write the injection code, the code that is making this parasite code work. So, of course, we include that header that we just generated, and then we do the same thing as with syscalls. Like with stop task, we prepare the compel, they prepare the victim. Then we do some other things like parasite setup. C header is doing some magic to link the parasite. Then we run compel infect that actually infects the victim with this parasite code. And then we prepare the arguments, supplying the type of the arguments. It could be like int. The type here could be int. And then we initialize that. In this scenario, we're going to close file descriptor number 42. And then we do compile RPC called sync. We supply the command, and and that's it. The argument is already initialized. The argument passing is through the memory. You cannot pass it any other way. Once you're happy with executing those calls, you can do as many as you like. You can do it for threads, and I'm not going to cover that. And you can do it in a sync or async manner, and I'm not going to cover that either. Once you're happy with your parasite work, you cure the victim and you let it continue. And this is what we do during the checkpoint stage. Can I have the next slide, please? Open Office. some constraints about the parasite code. There is no libc in there. Libc is in that is most probably it's linked to that binary, but we have our own code and it's not linked to libc. So there is no string functions, there is no memory functions, there is no printf. You cannot do anything from there, even call the syscall. So the solution is we have some very small libraries that we call plugins that lets the parasite do some actual real work. And we have the standard plugin so far, which is linked by default, and with that you can do system calls. And with that you can do strlen or memcopy. And it also has some probably ugly and basic printf and vprintf and so on implementation. So it's not usual C then you write parasite code, but we try to make it as good as possible. The other plugin, which is still work in progress, it lets you to set up a shared memory region between the parasite and the master process. It's still not ready for prime time. Anyway, there was compel, and compel you can use it for some things, and I'll just give a couple of examples here. You can do log rotate without application knowing about it. So you can just close file descriptor, copy the file over, open it, and then keep the application running, and your log is rotated, even the application is not supporting it. You can monitor process from inside. For that, the parasite needs to clone itself, so it will keep running, and then it will have some pipe and report some vital stats about the application, being that application, being a thread of that application. You can update an application, just like a runtime patching of the application that can probably be used to patch a security hole without, restarting everything. And I know that big vendors like Amazon, they have problems with that. They cannot restart everything immediately, and once some next dirty cow will surface, everyone is having a big problem. So we had a guy who's trying to work on that, and that means you can change some code inside the running app, or you can relink it to a new version of libraries once these libraries are available. And then finally, you can probably have some application that works badly and has memory leaks, and then little thread of yours can do freeze and cure those memory leaks, so you can keep this cripple thing running forever. There's much more, again, CRIU.org/compel usage scenarios. I hope you have some questions. Is that it? No more questions? Yes?
Docker documentation that I saw said something about not yet supporting freezing with interfaces. Did they mean like with X Windows? I think freezing a terminal application.
We work with TTYs, so we work with terminals. About X application, I think we work with X application as long as it's not X server itself. If it's just some X application, it uses some standard mechanism, so we can checkpoint it either. Well, of course, we cannot checkpoint and restore everything. That's sort of like it can be a problem. So one thing you can do is to give it a try and see if it works for you. We support more and more cases with every new release. Like, for example, we were not able to checkpoint and restore non-established TCP connection. That is like in a final state, or it's like in the pre-accept state. And we still have to have a couple of memory patches to do that. We cannot checkpoint and restore everything that deals with some real hardware, because part of the state is in the hardware and we cannot, checkpoint and restore it. But it works for lots of things. I mean, worst case scenario, of course, is you checkpoint something and then you try to restore it and it fails. And if you killed it, that means you lost it. So the way to fix it is to keep it in a frozen state unless you make sure you have restored it and it works. So this is how live migration works. It keeps the source in a frozen state unless this thing is fully restored. Once it's restored on the destination, it gets killed on the source. And if something is not working, we still have the source frozen, which we can unfroze and say, well, it didn't work, but nothing is broken. Any other questions? Yes. I believe it's like from 3.10. That is pretty old kernel by nowadays standards. Yeah, you can use CRIU with that, and then we can have CRIU tech command that tells like which features are supported and which features are not supported. It probes the kernel, and we can have its CRIU.org/upstream kernel commits page, which lists each and every patch that we merge into the kernel and what it does. I said it's about, I think it's 201 patches so far. So, but yeah, again, the best way is just to give it a try and see if it works for you. And if not, we are here to help. I'm here to help. This is my contacts here. It's either Kolishkin at Twitter or Kier@openvz.org. And CRIU also has its own Twitter. And we have pretty good community as to, help each other. Any other questions? Yes. Well, I doubt that. You mean GDB as new debugger? No, you cannot run your own code inside a foreign process context. You can just take a peek at what's there. You cannot just, close the file descriptor. You can just see what's there. You can stop it, you can analyze it, you can see the variables, but that's about it. You had a question, please? Well, Docker is a good example. You do Docker checkpoint and Docker restore, and inside it's all CRIU. I can't think of any at the moment. All right. If there are no more questions, thank you everyone for coming. I hope you enjoyed it.